said it's my pleasure to talk at the Princeton and the Institute in my office in Beijing. Okay, so it's about this uniform Mordell-Lang and the uniform Bogomolov. So before I talk about the math, I want to mention some a little bit about how I arrived at this this new proof of the Mordell-Lang, uniform Mordell-Lang. So many years ago, that's even more than 10 years ago, Shou and I had a collaboration on this Hodge index theorem for adelic line bundles. And then at that time first we did that over number fields. And then that was based on the old theory of adelic line bundles over projective varieties of Shou. And then to extend it to finally generative field, we got a new theory of adelic line bundles. But that was 10 years ago. And unfortunately, our writing was very technical, and our paper was rejected 10 years ago. And then just in recent years, we started to rework on the theory. And in the meantime, there was this breakthrough on the uniform Mordell-Lang by Dimitrov-Gao-Habegger and Kuhne. So when we did our adelic line bundle, and they had their breakthrough, and then we realized that we can really connect to what they prove and use our new terminology, new theory of adelic line bundles to prove many parts of the key results in their proofs. So that's eventually written as a book by Shou and me. The new version was finished in May this year. So that was old version was 10 years ago. New version was done in May this year. And then after that, I realized that I can even use this new theory of adelic line bundles to give a completely different proof, independent proof of the result of the uniform Mordell-Lang result. So now here I'm going to talk about this completely new proof. Okay, so mathematically, I will first talk about the uniform theorems. And then I will recall a little bit about the adelic line bundles. This is the new theory of Shou and me. And then I talk about this bigness of admissible canonical bundle. And then I talk about the idea of proof. Okay, so let's start with the uniform theorems. So let's start with 14th theorem, which is the Mordell conjecture. So suppose K is a number field. Suppose C over K is a curve. And genus is greater than 1. So of course, we require a curve to be projective and smooth here. So now, then the theorem says the number of rational points is finite. So this is a well-known marvelous theorem. And the topic today is about uniform bound on this finite set, on the order of this finite set. So the uniform Mordell theorem is this is due to Dimitrov-Gao-Habegger and Kuhne. So it says there's a uniform constant Cg I should have used different letters. So let me change my curve to X. So now Cg is a constant Cg, depending only on G. G is the genus. And then now such that the number of solutions is bounded by a power of Cg, and the exponent is the rank of the Mordell-VE group, and then plus 1.
So you still X of K, right? Because you changed C already.
Oh, X again, yeah.
And C is effective.
Not yet. So we probably if we work really hard, eventually maybe we get effective C. But for the moment, it's not effective.
Okay, thanks.
Okay, so so that's J. J is a Jacobian. Okay, so this is a pretty clean result, and this confirms a conjecture of Mazur. And there are many other conjectures on this uniform bound. Even they have even much stronger conjectures. For example, it says that the uniform bound should depend on only on G and the number with K, even not on the Mordell-VE rank. But I'm not gonna write it down. So now I'm gonna talk about the idea to get a bound. So from the proof of the Mordell conjecture by Vojta, it is natural to bound the points according to the size of the height of the points. So here is like we first bound the number of big points. Big means the height is big. The Larentate height is big. So that means when we consider X in XK such that the height, the canonical height of X is greater than, here we put some multiple of the 14th height of X. Oh, this is little x. This is big X. Okay, so epsilon is gonna be a constant depending only on G. Maybe still we need put some other constant, but roughly it's like this. So this is this has explicit bound. The number of points has explicit bound by Vojta. So Vojta gave another proof, the second proof of the Mordell conjecture, and also a pretty new proof, like a third proof, is given by Ashay. So this is Lawrence and Venkatesh. Okay, so now for the bound here, it's most related to Vojta's proof, and Vojta's proof was simplified by Bombieri. Actually, Bombieri's simplification is also based on 14th simplification, and then the explicit bound along these ideas of Vojta and Bombieri, the bound was obtained by Diego and Riemann. So this for the number of big points. That was done like 20 years ago. Now the major focus here is the number of small points. So that's gonna be x in xk, such that this height is less than some epsilon. This epsilon may be different. But eventually it's fine. Even if epsilon prime is different from epsilon, there are some elementary ways to eventually get rid of the gap. So this is not the major issue here. So now this number of small points, this bound is by Dimitrov-Gao-Habegger and Kuhne. And then this is eventually the uniform Bogomolov conjecture. Because the Bogomolov is about small points of small height, and the uniform means we want to vary the curve x. All right. Yes. Okay. So now I'm gonna recall the Bogomolov conjecture briefly, and then talk about the uniform Bogomolov conjecture. So recall this Bogomolov conjecture. Ulamov theorem. Ulamov's theorem, Bogomolov conjecture. So the setting is still as above. C is over K, G is X. G is greater than 1. And then it says there exists epsilon greater than 0, such that when we put X into the Jacobian and compute the height, it turns out that there are only finitely many points of height bounded by epsilon. So such that for any x0 in divisor of x k bar, so we take a divisor of degree 1. So I put 1 here. You can think x0 just as a point, and then now we want to use x0 to embed it into the Jacobian and compute the height. And now we take x in xk bar, and then when we embed it in the Jacobian, we get a point x minus x0. We get a divisor of degree 0. Then we can take the narrated height. Now it says that one less than epsilon, then this is finite. So if epsilon equals 0, then we get just torsion points under the embedding. But now it says even slightly relaxed we get like the number of small points is finite. So this Yuan theorem, it is proved in terms of the equal distribution theorem of Shapiro, Yuan, and Zhang, and it was further extended to sub-varieties of abelian varieties by Shou Zhang. So now I'm gonna talk about the uniform Bogomolov. So this is the new part, the new recent theorems, which gives the uniform Mordell-Lang combined with the old results of Voigt et al. Okay, so now the theorem says there exist constants C1, C2. These constants depending only on G. And such that for any curve x over q bar, this is gonna be a curve genus G, and for any x0 in x q bar, so this is a point on x. Now it says now we are gonna bound the number of small points. So this set is as in the original Bogomolov conjecture. Now on the right hand side, we use this C1, this constant C1. And we want to put, instead of a pure constant, we want to put the furnace height inside. So the furnace height of the curve is defined to be the furnace height of the Jacobian. This was exactly the height used in 14th proof of the Mordell conjecture. Roughly speaking, we can think the furnace height to be the height of the coefficients of C if you embed C, for example, by the canonical embedding into projective space. Coefficients of the equations. All right, so this gives the bound. So let's look at the bound. The constants C1 and C2 are here. So we get the height. We want the height to be bounded by a multiple of the furnace height. And then we still want like the total number is bounded. So the key part, of course, is that C1 and C2 are independent of, depending only on G, independent of the curve X, also independent of X0. So it is straightforward to use this uniform Bogomolov to imply the uniform Mordell-Lang. If we go back a little bit, so we see here, we need to bound the number of small points. So it's really we want to bound the number of points, of points of height bounded by the furnace height of X. So it's exactly this bound. Okay, so now I'm gonna, before I talk about like the proofs and like the ideas, I'm gonna state my theorem. So my theorem is also in this style. It's a uniform Bogomolov. But I have like generalized and also strengthened this theorem in many aspects. So still we have G greater than 1, and still we have C1, C2. So now, now I'm gonna change the base field to allow it to be any global field. So now I add one term, one line about the base field. So for any k equals q, or k equals little kt, because I want to allow function field. So so this is just like to include all function fields. And this little k, I don't put any restriction on this little k. So now for any x over k bar, so curve genus G. So this is the same. Now in the next one, I extend it a little bit for any x0 in. So if we look at their x0, they take x0 to be a point. But if you look at unimals x0, x0 is actually a divisor. So unimals theorem is like more general in that sense. Now I'm gonna allow x0 to be a divisor of degree 1. I'm gonna use pick, because later on I need to talk about isotrivia. So pick degree 1. So this is about x0. Now I need to put a condition about isotriviality such that this x0 is non-isotrivial. If k equals kt. This is a natural assumption for function fields because I allow function fields, so that occurs. So that just means the pair x0 together cannot be descended to little k. Okay, so now finally the inequality. The inequality is also slightly different. So I will put C1. C1 is still C1. This 14th height term is still here. But then I'm going to put another term. So this term is about the height of, essentially like height of x0. So I will put the height of x0, but x0 itself, like we don't have a canonical way to define the height. We need to make it something of degree 0. So we'll use the canonical bundle to get a degree 0. So that is 2g minus 2 x0 minus the canonical bundle. Now, this one gives a divisor of degree 0, then we can talk about the narrated height, like the height of the point in the Jacobian. Now this whole thing together is like we multiply that one by C1. So this is the right-hand side of in the set. Now it's bounded by C2. All right, so this finishes the statement of my theorem. So now we can compare my theorem, like my assumptions, with their original theorem. So now there are like a few parts, a few extra parts. So the first part is I allow K to be a function field. So, and even K can have positive characteristic. So this characteristic of K is greater than or equal to 0, can be positive. So this is the first difference. Now the second one is about this pick 0, now pick 1, as I already mentioned, this pick 1 comparing the point. So now the third one is more substantial. The third one is this extra term. This extra term, this is non-negative, mostly positive. So this extra term is here, then of course it makes the result much stronger. Okay, so that's the theorem. So I also remark that my constants C1, C2 are even uniform, even if the characteristic of K changes from P to Q, the constants C1 and C2 are also uniform. All right, so now I'm gonna talk about like the.
So you mean C1, C2 does not depend on small k?
No, does not.
Okay.
I have
Does
a
not.
question about your function field.
Yeah.
So your theorem does not handle, for example, if capital K is the function field of an elliptic curve over a finite field.
So, oh, you mean that that's also included because eventually X is over K bar. So X is over. You look at here. This is K bar. So
Okay.
that includes all function fields.
Okay, see you. And then second thing is like you can recursively apply this K of T where little k is also a function field to get like any transcendence degree. Is that right?
Yeah. We don't need to apply recursively. It's just we just take a subfield of such that the extension has transcendence degree 1.
Yeah, but it is the height depends on k.
Oh, this
right?
oh right. This height depends on the choice of little k. Yeah.
So
Okay.
because it is
Okay.
defined by intersection theory and a
Yeah,
surface.
yes. Okay, so the ingredients. So so maybe first ingredients of DGH and Kuhne. So so first they need this non-degeneracy result. Of subvarieties of abelian scheme. So this is the most exotic part to us because this requires model theory. So this requires O minimality. This type of results were proved by Gao in some 2 separate papers. So because of that, because they need O minimality, this is like similar to the proof of the Andre-Oort conjecture. Like you use O minimality to relate algebraicity of the Schmer variety. Here is subvariety of Schmer variety, or here is like subscheme of abelian scheme with algebraicity of the universal cover. So then that's like, that really requires a characteristic zero. So now the second ingredient is a height inequality of DGH. So they proved a height inequality based on the Lang degeneracy. This height inequality is comparison of the height of a point on the curve and height of, essentially like height of the point of the curve and the 14th height of the curve. So now the third one is like an equidistribution theorem. So Kuhne proved an equidistribution theorem. So the equidistribution theorem extending, generalizing, the equidistribution theorem of Shapiro, Yuan, and Zhang. So now the fourth part is like a family version of argument of Yuan Zhang. So the original Bogomolov conjecture was proved uniform and generalized to subvarieties of abelian varieties by Zhang. And then the argument of Yuan and Zhang is to use equidistribution theorem eventually to get a contradiction. Now, the proof here is similar. So they get a family version. You can see that they get a family version of this equidistribution theorem. And then they get a family version of the equidistribution argument. So it's just like make everything in family. So this is their proof. And as a remark, as I mentioned at the beginning, so the adelic line bundle of me and Shou. So the new theory can be used to reproof or like independently prove some results. So proves the height inequality and also proves the equidistribution theorem. So with like our proof is more theoretical if you assume this technical theory of adelic line bundles. So, and this one is independent of Kuhne.
How about point 1, where you use O minimality? Do you avoid that?
Yes. I avoid it because I need to do positive characteristics. So that's also avoided. Okay. So okay. So now about my proof, I also give like ingredients. So the most important thing is this adelic theory. Adelic line bundles. Okay, so now also the key part, the key proof, like the key results here is the bigness of this admissible canonical line bundle. So the admissible canonical line bundle is like an example of adelic line bundle in our new theory, and I proved that it is big for the universal family. I will talk about that briefly later. And then another new ingredient is this. Also, we also need some height inequality to compare height. So this 3 is similar to this 2. This one is similar to that one. But actually we have like we get a stronger version of height inequality. Now this based on bigness. And there's this Sue's theorem. And this arithmetic version by me, some bigness result to this is now standard to treat, to compare height of different big line bundles. So of course the key part is that the key part as asked by Peter. So no need to use no or minimality. And the proof is good for all characteristics, 0 or P. So it's mainly intersection theory. All right, so that's about like the theorems in differential geometry. Now I'm gonna briefly sketch some parts of the proofs or some theories. So now the second one is about adelic line bundles. So the definition is quite involved. So I just give some quick ideas. So assume K is a lumber field. Now assume X over K is a quasi-projective variety. So the original theory of adelic line bundles is about projective varieties by Shou. Now the new theory can do quasi-projective varieties. So now we have this L bar. We put L and we put matrix. We put all V in MK. So this is called matrix line bundles. So MK is all places of K, of course. So here L is a line bundle over X. And this one is a metric. So it's gonna be a V-adic metric. So I'm gonna take the Berkovich space. Berkovich space. If V is Archimedean, then it is just the usual complex place. Now we require this metric to be continuous. Or maybe if you're not familiar with Berkovich space, you just think about this set, metric over this set. This is totally disconnected, but for the purpose here, it's actually okay. So it works like roughly. Okay, so this is the matrix line bundles. So now we talk about models. So we put X here, L bar here. a model of XL over OK. So it's a model if we have, so first we have X is going to be a model of this curly X is a model of the usual X, but then usual X is quasi-projective. So basically we want that one to be open sub variety. So curly X, we take a generic fiber. The generic fiber of curly X compactifies X, and then we compactify the generic fiber to curly X. Oh, sorry, I didn't mention that one. So I didn't mention this one over OK is going to be projective integral flat. So now this L bar is a Hermitian line bundle. Over X extending L. Now, now this data induces a matrix line bundle. As in here, as in this one. So basically this one induces this one. Induces a matrix line bundle over X over K. Okay, finally our adelic line bundle. It's like we also have this. Let's call this one. Let's call this one model called model matrix line bundles. So adelic line bundle over X is going to be a limit. We define it to be a limit of model matrix line bundles. Over X. So then the key thing is, this is still over X. The key thing is about this limit. So there's a way, we have a canonical way to define the limit. We define a topology, and then topology, essentially topology on the matrix, because the matrices are analytic terms. So it's more natural to consider limit, easier to consider limit. And then under the topology, we can talk about limit. So so roughly speaking, adelic line bundles are limits of line bundles over projective models. Okay, so as you can
Sorry,
see,
there's a question in the, oh, okay. I was going to say there's a question in the chat. Does a curly L like this always exist?
That's the
sorry,
definition of quasi-projective, right?
Yeah.
Quasi-projective means it's open subsets of projective one.
Oh, you need to do two steps. I see. You first do curly XK, and then you do curly X. Okay, so adelic line bundles are just limit. So this new theory of Shou and me is about limit. It's really to take a limit. Later on, we will see like why do we care about limit. So the remark is that projective case is by Shou's original work. Okay, so that's adelic line bundles. Now we talk about the admissible canonical line bundle. So this is an example of the adelic line bundle. So now we'll start with a family of curves. This is already close to the setting of the uniform Bogomolov. So we start with x over s pi. So this is going to be a family of curves. So let's say K is still a number field. And then S over K is quasi-projective. And then X over X is X over S is smooth projective. And then fibers are curves. Curves of genus, say we fix G greater than 1. So this is just a family of curves. So the most important example is S equals mg, the modular space of curves. Or maybe you want to put some level structure here to make it really a scheme. So actually in our application, we do use the modular space to prove it holds for every curve, means proof it for the family for the universal curve over the modular space. Okay, so now I'm gonna put it into the Jacobian. So now suppose J is the relative Jacobian. So J is over S. So it's just the relative pick zero functor, or maybe just think it like on every fiber you have the Jacobian variety, and then you patch them together. So now I'm gonna take an embedding, actually a map instead of an embedding, a finite morphism. So I call it little j. I map x to j. Usually we need to take a base point, but here we don't have a base point, so we just use the canonical line bundle. So we map x to 2g minus 2x minus the canonical bundle. So 2g minus 2 is to make the degree 0. So you can view this map like defined fiber-wise, and then they are algebraic. So this J is a finite morphism. You can just think of it as an embedding is fine. Okay, so now here I need some fact. So the first one is there exists a line bundle theta over J. So this theta is like symmetric, relatively ample, rigidified. And then finally, like on fibers is twice. On fibers, it's twice of theta divisor. So on each fiber, we can talk about theta divisor, and then, sorry, not algebraically equivalent to, because we don't have a base section, so we can't get exactly theta divisor. So, but twice of theta divisor always exists, canonically exists. So now the second remark is like an isomorphism in pic S. So the isomorphism is we have this omega x over s, the relative dualized sheaf. Now that's gonna be 4g, g minus 1. We pull back this theta, and then we plus some multiple. So so roughly it's just as when we pull back this theta, we get that relative dualized sheaf. But then there's this error term. The error term, this is like pullback of something from S. So this theta is the Delim parent.
Your left side is a bundle of X.
Yeah.
Is
No,
isomorphism of X.
over X. Oh yeah, X. Yeah. Yeah, XQ. Just tensor some power to clear the denominators. We get a true isomorphism. Okay, so this is classical, at least like the absolute version. When S is a point, this is like a well-known result. So now, once we have that, we define, finally, we define the admissible. This is our admissible canonical line bundle. We define it just using this formula. This is not quite the definition, but it's equivalent to definition. So we just write it in here like this. So again, this is like the limb pairing. So this is adelic line bundle over X. X is also like, X is quasi-projective. S is quasi-projective, so X is also quasi-projective over capital K. Okay, so I need to explain this theta bar. So what is the theta bar? So this is the part we need limit. So we have this theta is in this pic X. X over X, sorry, is J. The abelian scheme, J. And then it is symmetric and rigidified. So that means when we do the dynamical pullback, we will get 4 times that one. 4 times means like tensor fourth power, but I write the tensor additively. So this is by the symmetry and the rigidification. And then by this Taylor's limiting argument, as you pass from naive height to canonical height, when you have naive height, you want to define canonical height, you need to iterate and take a limit. Here, the same thing. We iterate and take a limit. Eventually, we get something canonical. So we get a unique theta bar, this adelic over X, such that we pull back, we still get the nice property.
Over the J.
J, yeah. Thank you. Yeah. So this is the very reason we need to take a limit to get a single line bundle instead of a sequence. Okay, so then as you can see, this degree of theta bar over points of JK bar gives canonical height, the Laurentide height. This from the iteration Taylor's limiting argument. So now we see like this omega, the admissible one is more or less just pullback of theta. Just like we have this theta bar, we pull back. Now finally I can extend the state my bigness theorem. I want to say this omega is big. So omega is like the pullback, and with some like tail. The tail is the limb pair part is a minor part. So now the bigness result says this canonical bundle is big. Big is like, in our definition, we can still talk about sections, volumes, and then big means like we have plenty of sections, effective sections. So but I need to put one minor assumption, natural assumption, assume this S goes to MG. So the map to the modular space, we assume it is generically finite. Now the result says then this omega X over S bar, this is big over X. So again, big means plenty of norm effective sections. Okay, so I'm gonna remark. So the first is for any, if we take any point, letter S in S, close point, and then we do this omega restricted to the fiber, restricted to this XS, the fiber. So that's like omega XS, letter S. That's the usual curve over a lumbar field. Now this is like the original admissible canonical bundle of Shou recovers over lumbar fields. So now the second remark is in this absolute version, or maybe let's say the fiber version, this one is greater than 0. That's just like the bigness. Greater than 0 is like the bigness in fiber version. This is equivalent to the Bogomolov conjecture, the conjecture proved by Unimo. So this actually gives another approach to prove the Bogomolov conjecture. This approach, this equivalence is also by Shou, the equivalence. And then this proof is this path, just like this independent proved by Shou. So like a second proof of the Bogomolov conjecture without using the equity expression theorem by Shou, Sinker, and Robin de Jong. All right, so now I'm running out of time. So now the proof of the bigness is just a family version of, you can imagine, family version of this argument. So they have an argument on fibers. Now I need to do it in family. So eventually it works out to get bigness over the family. So I don't have time, but I'll use like a couple of seconds to talk about the idea of this uniform Bogomolov. So we still have this X over S, just like the family of curves. And then we have this J, and then we have this theta. And then we pull back, we roughly get this omega. Pull back. There's a tail, but let's not worry about the tail. So now the uniform Bogomolov roughly it's implied by the fact that this omega X over S. Let me write one more step. So uniform Bogomolov is like, we want this height of that one to be big, or at least outside some sets, it is big, it's positive. So this is Bogomolov, uniform Bogomolov. This X is in X K bar. Now then when we pull back, then then it's the height of this one. I will just write it as omega bar x is big. Because omega bar is just pullback of theta bar. This is by the projection formula, they have the same height. Now this omega bar is big. This big is different millions, like plenty of sections. But plenty of sections eventually implies the height is big. This implies the height is big by this. I can write a little bit, that's fine. So it's big, then it says there is this sections S of probably like some power up to some power of small norms. And then this height of omega bar x, that one, if we compute in terms of this section x, it looks like this. Roughly like over all places. And then the norms are small, then that one is gonna be big. Greater than some epsilon, greater than 0. And then this is for x in xk bar outside the 0 locus of S. Also k bar. So this is Zariski closed. Outside a Zariski closed set, the height is big. So then eventually, of course, this is just the rough idea. Eventually, we can rigorously make that one really work to get the uniform Bogomolov conjecture. All right, thank you very much. I'll stop here.
Thank you, Xinyi. Let's give him a round of applause. Right, so are there any questions?
But how do you prove that's big?
So actually, so remember this omega is J pullback of theta plus, let's see, where is it? Yeah, plus some theta. But then by this, we can also get like J pullback of theta plus some multiple of omega up to some multiple lambda greater than 0. It's just like once we have the first inequality, we get theta is some multiple of omega. Oh, no, not theta. Sorry, that's like, oh yeah, it is theta. So and then this one is nav, and then this omega is also nav because theta is nav. That's because theta is nav. So everything is nav in here. That the imperium of nav is still nav, and then now it's omega. That one is big. Actually implies omega is big. This is by this one. When we take by this one, we take the top intersection.
Right.
So we have a tail and this theta on fiber. Theta on fibers is already ample.
I see.
So this is by top intersection. And then so it's reduced to prove this the limb pairing is big. This big is over S, the base S. And then eventually we prove this, we compare it with the Hodge bundle. So we prove that one equals lambda s bar, just lambda s bar here. This is the Hodge bundle. The Hodge bundle to define the Fulton's height. On this S or maybe on MG. And then plus some error terms. These are like net or effective. And then this one is big. This one is big. This is more or less like a classical result.
So this is 12, right? There's a Noether's formula. Omega bar
like
12.
Yeah, Noether's formula is used here. Yeah. But it's part of it.
Okay.
Yeah, Noether's formula says like 12, but then the error there is not effective. So we need like some other ways to combine eventually to get rid of the error part. Yes. Actually, this is not, there is a constant here. It's not 12, like, because I need to replace it to get effectivity and neatness.
So it's not an equality, it's an inequality, right? What do you?
Because I put plus, then it doesn't matter.
Okay.
Well, are there any other questions?
Yeah.
Okay, if not, I have a, oh, sorry, go ahead.
Thanks. Is there a hope to do a similar bound like for the big points so that it's compatible with the small points, and then like will actually, so maybe over some of the fields?
You mean for the first part, like for this one? Big points?
Yeah.
No, there's no easy bound for this part. So these two parts are treated very, very differently. So the first part, Voitov's proof, is by finding approximation. Like it's just very, very different. And his proof is also like non-effective in the sense that we don't have a bound on the height of the points. We only have a bound on the number of points.
Thanks. So like so even over K of T or something like this, like that wouldn't, like there is no analog of this.
No, it's just different. At least from what we know, it's very different type of techniques, theories.
Thanks.
Any other questions? So I have a very basic question. To get your theorem over fields that aren't, well, number fields, is this just some standard reduction using like the coefficients of everything that's being defined here? How do you get it over function fields over an arbitrary field?
Oh, so yeah. So in my writing, at the end, I assume K is a number field, but actually the proof like works similarly for function fields.
Oh, okay.
Yes,
you still have this adelic set up for these fields? Okay.
Yeah.
I see.
Yeah.
Cool. And another question, this not isotrivial assumption, it's pretty clear that the theorem is going to fail if you don't have it, but how does it actually get implemented in the proof?
You mean how to?
Yeah, where exactly does this end up getting used in the proof?
Oh, how is it used? Yeah. So it's we can look at one example, just like we look here. So look at this bigness theorem, this assumption of S to mg is generically finite. So it's actually used here. So you can imagine if you have like a so I write a little bit. So this k is kt now, and then now you want to map to mg of little k. Your S is like mapped to little k. Now you can extend. Suppose your S, you extend your S also to k, and then you have like a curve to k. You just think S is like a function field. So this ks is k. You have this curve. Now if this curve is isotrivial, then the image is going to be a point. The image of this modular map is a point.
Right.
Then it's not generically finite because S is a curve. So we want it to be generically finite, then we want to avoid isotrivial.
Great. Thank you.
Mm-hmm.
Yeah. Are there any other questions? Well, if not, we can thank Xinyi again, and I guess we can stop the recording too.
Thank you.